Hello everyone. So today we're going to continue on 6.3 implicit differentiation. So last video we get to do this example right here, which we try to find dz over dx and dy over dx. And remember what I mentioned to all of you, when you're doing these type of problems, you have to make sure you pay attention to what the problem asks you to use as a dependent variable versus independent variable, because it changes the way the problems work and also changes the partial derivative that you're looking for. So I'm going to basically do the same exact problem, but I'm going to now define the function in a different way. And you will see that then you will get completely different answers. So imagine the following. Imagine we have the same equation. Let's say given x squared plus y squared plus z squared equal to sine z. But this time we're going to assume that x is a function of y and z, and therefore changes the partial derivative we're looking for. So now I'm going to ask you to find dx over dy and dx over dz. So notice that the partial derivative is different than before, especially because we now define the function a different way. In this scenario right here, we are defining x to be the dependent variables, which I know is kind of weird. We usually don't do that. But then in parametric we do. We're choosing x, y, and z to be our independent variable. So what will happen to our equation? Well, same way, we go do the same thing. So first we go do is this. We go first, how about we find dx over dy first. So to do that, I'm going to basically take the derivative with respect to y of the entire equation. So therefore, it's basically the same thing as taking the derivative with respect to y of x squared with respect to y, y squared, the derivative of y with respect to y, z squared, and then the derivative with respect to y of sine z. So now here where you have to pay attention and be careful, x is a function of y, therefore when I take the derivative with respect to y, I have to use chain rule. So this becomes 2x dx over dy. When I differentiate with respect to y, y squared, then it's just the function in terms of y. So I'm just going to basically differentiate without actually the need to use chain rule. So that would be 2y. And now what happened when I differentiate with respect to z? Now this is different because z in this scenario is a independent variable just like y. And in partial derivative, we treat other independent variable as constant. So when I differentiate z squared with y, this actually comes out to be 0. And so what happened to sine z? Well, sine z is also a function of z, which is independent of y, and therefore treated as constant. So therefore, that also equals 0 on the other side. So therefore, if I'm looking at this correctly, it seems to me that dx over dy would just equal to negative y over x. When you move the y over and divide by, when you cancel out the 2, which is probably the first thing I'm going to do, and then just move the y over and divide. Notice that's definitely a different answer compared to before. And I would strongly recommend that you take a minute to pause the video and try to see if you can find dx over dz and see what you got. Okay? So I'm going to continue. So I'm going to go and pick the derivative with respect to z of x squared plus y squared plus z squared equal to sine z. So therefore, when I take the derivative with respect to z of x squared, that becomes 2x dx over dz. What happens when you differentiate y squared? Y squared is considered to be constant when I differentiate with respect to z because y is another independent variable. So that just becomes 0. And then z squared, when I take the derivative, that becomes 2z. And derivative of sine z is cosine z. So now I'm ready to find the derivative. I'm going to go and move the 2z over. So 2x dx dz equal to cosine z minus 2z. And then I'm going to divide it by 2x. So dx over dz equal to cosine z minus 2z over 2x. So notice that's definitely different. It's similar, but different than the answer that we got. Okay. Interesting thing to note, notice that dx over dz is actually the reciprocal of dz over dx. That's kind of interesting. So now this two example can illustrate what happened when you try to find the partial derivative, when you define the implicitly defined function. But there's a little tricky about it. When using implicit differentiation, with vector value function of several variables, so meaning function that have multiple independent and dependent variables, you often run into the scenario where you actually end up having a system of equation. And so what I want to talk about would be how to deal with that. So often end up with a system of equation. Now you might be thinking like, how is that going to happen? So obviously I'll show you an example to kind of illustrate what that means. But the problem here that I want to talk about before we get to an example is the following. Since a system of equation can have either no solution, one unique solution, or infinite solution, what we want would be some unique formula that can allow us to define the partial derivative. So therefore what we want is really a unique solution. And based on what we learned in chapter 2, we know the following. Since a system of equation can only have a unique solution if the coefficient matrix is a square matrix. What we want to do is provide condition that would allow this to happen. And this is what we need to know. We need to have the same number of equations as the number of, very important right here, dependent variables. So therefore, the number of equations we need is dictated by the number of dependent variables that we have. So the more dependent variable we have, the more equation we need. So if you look at the previous two examples that we have done, notice that these two examples both have one single dependent variable, which is x, or in this case, which is z. And because we only have one dependent variable, we only need one given equation to work with that. Now, if either of these two problems, we choose to assume multiple, let's say 2 variable as a function of a single independent variable, then it would not work out for either of these problems because we don't have enough equations. Now, to fully understand how that works out, it's probably best to see that in an example. So let me show you a very simple example to illustrate. So this one is extremely simple because the derivative come out to be relatively straightforward. So show you. Let's say given that x plus y minus u minus v is equal to 0, and x minus y plus 2u plus v equal to 0. Assume, so here's one of the important statement right here, we're going to assume that x and y are functions of u and v. I'm going to ask you to try to find all these partial derivatives. dx over du, dx over dv, dy over du, du, and dy over dv. Now, first let's understand what it means. So when I say x and y are function of u and v, what does that imply is the following. It implies that in this scenario right here, x and y, they are our dependent variable. There are two of them. And u and v, they are our independent variables. Because we have two dependent variables, we have to have two separate equations that define the relationship. Otherwise, we'll not be able to properly figure out what's going on. Okay? So, what does that mean? When I say x and y are dependent variable as functions of u and v, that implies that x is equal to some function x of uv, and y is equal to some function y of uv. So it doesn't mean that x is a function of u and y is a function of v. It means that x is a function of u and v, y is also a function of u and v. Now, then how do I actually find these derivatives? So we actually don't find them individually. We actually find them in pairs. Okay? What I mean by that, because you have to differentiate with the same independent variable, but across multiple dependent variable, you will find them in groups of each other. So let's start with our first thing. We go try to find dx over du and dy over du. We find both of these together because they're using the same exact independent variable, therefore it differentiates the same way. So this is what we're going to do. We're going to basically take this first equation that we have, and we'll differentiate it with d over du, with the variable u. And if I do that, what I'm going to get will be the following. What I'm going to get would be, I have derivative of x with respect to u, that will be dx over du, plus derivative of y with respect to u will be dy over du, minus derivative of u with respect to u is 1, and derivative of v with respect to u, since v is another independent variable, will become 0, equal to 0. Notice this gives us an equation that involves both dx over du and dy over du. Which is the reason why we have to find them together, and that's the reason why we go result in a system of equation. Now what I'm going to do is the same thing, but now I'm going to differentiate the second equation with u. So that comes out to be dx over du minus dy over du plus 2 plus 0 equal to 0. So therefore become dx over du minus dy over du plus 2 equal to 0. So notice now will result in a pair of equation where we have two partial derivatives we have to look for. Okay, and it makes sense in the following way, because we have two partial derivatives to look for, and we do need two equations in order to properly solve for them. Which is the reason why, I said that you will need the same number of equations as the dependent variable in order to do it. So that's just a matter of solving these two equations, so it should be pretty easy to do. In this case, I'm going to just go for it. I'm going to take the top equation and the bottom equation, and I'm going to just simply line them up, and then I'm going to add them. When I add them, what happens is these two things just cancel out, therefore leave me with 2 dx over du plus 1 equal to 0. And so that tells me dx over du must equal to negative 1 over 2. So notice that this gave us a constant, therefore implying that dx over du doesn't change. Then what should dy over du be? Well, it's up to you how you want to solve it. I think the easiest way to do it is the following. I'm just going to puck into one of the equation. I'm going to say negative 1/2 minus dy over du plus 2 equal to 0. I'm going to move the dy over du to the other side. And then I just have negative 1/2 plus 2, which is 3/2. So therefore, I can say dy over du is 3 over 2. Now what we can do is now find dx over dv and dy over dv. So number 2, let's try to find dx over dv and dy over dv. So once again, you're finding both of these together also. So what do I do? Same way as before, I'm going to take d over dv off my first equation. Oops. And that result in this equation, dx over dv plus dy over dv minus 1 equal to 0. I'm going to take the derivative of the second equation, x minus y plus 2u plus v equal to 0. So that come out to be dx over dv minus dy over dv plus 1 equal to 0. If I add these two equations together, notice that dy over dv cancel out, so does the negative and positive 1. Therefore, just tell me that dx over dv must equal to 0. And because of that, that tells me that dy over dv should equal to 1, because 0 plus 1 minus 1 equal to 0. So those are our answers. Now notice that how it turned into a system of equation. That's what you're going to run into when you try to solve this equation. Solve for the partial derivative implicitly. Important to realize is what is a variable, what is a constant, when you need to do chain rule and when you don't need to do chain rule. Those are usually where students get confused. Now the next thing I want to show you is the following. Let's give you another example. Let's see if we can do this one. So this one will have even more variables to work with. And once again, it's just important to pay attention to what is independent, what is dependent, so they can properly solve for it. But this one a little tricky because I'm actually going to ask you to try to solve for it when we evaluate at a specific spot. So let's say in this case, let's say if or let's say maybe I would use this. Let's say we're given x squared plus yu plus xv plus w equal to 0. And x plus y plus uvw plus 1 is equal to 0. Let's say I give you these two equations. Okay? We're going to assume, in this case, we're going to assume x is equal to x of uvw and y is equal to y of uvw. So meaning essentially what does that mean? It means that x and y are functions of uvw in this case. What I'm going to ask you to do is the following. I'm going to go ahead and ask you to find dx over du evaluated at uvw xy equal to 1, 1, negative 1, 1, negative 1. And since we're doing dx over du, I might as well find dy over du also. And that would be, and yes, you cannot find one of them without finding the other one. Well, technically you could, but you would find both of them together because you have to solve a system of equation. At the same spot, uvw xy equal to 1, 1, negative 1, 1, negative 1. All right. Do want to point out the following notes. Hey, actually, you know what? Let's do black. Notes. Notice that I could also give you this. So this uvw xy is equal to 1, 1, negative 1, 1, negative 1. Basically imply that 1 is equal to x of 1, 1, negative 1. Or actually, maybe I just write it this way. Basically imply that when uvw is equal to 1, 1, negative 1. Xy is equal to 1, negative 1. So that's basically what it means. It means when you plug in 1, 1, negative 1, you get 1, negative 1 as an output. Because remember, x and y are a dependent variable and UVWs are independent variable. So now let's see if we can do this. Okay, so definitely a lot of things going on, but let's try to figure this out. So let's try to find our system equation first. To do that, what we're going to do is basically differentiate with respect to u of the two equations that we have. So let's go for it. So this is my first equation. I'm going to take it with respect to u. And here's my second equation. All right, so let's see what happened. If I take the derivative of x squared with respect to u, notice x is a function of u, so therefore chain rule need to be applied. So that becomes 2x dx over du. Now, what happened when I differentiate yu? Y is itself a function of u because that's what we define it to be. And u is definitely in itself function of u also. So therefore, product rule need to be applied actually. So when I apply product rule, I will have y times 1. Y times the derivative of u with respect to u, that's 1. Plus u times the derivative of y with respect to u, that will be dy over du. Plus xv. V is another independent variable. Therefore, in this case, act as like constant. So therefore, we basically differentiate x and then multiply that by the constant v. So therefore, that becomes v dx over du. Plus w. W is another independent variable, which when I differentiate with respect to u, it treated as constant. So therefore, that just go away. That becomes 0. Equal to the derivative of 0 is 0. So therefore, this turns into the following equation. 2x dx over du. Ooh, maybe I should write my 2 a little different. 2x plus y plus u dy over du plus v dx over du equal to 0. So that's my first equation. And we're going to do my second equation right here. So that derivative of x with respect to u is dx over du. The derivative of y with respect to u is dy over du. Plus, what happened to UVW? Well, u and v are both constant, so therefore we leave them. And what's the derivative of u? That would be 1. So therefore, that becomes 1 times uv. So therefore, it becomes just uv. I'm sorry, VW times 1 plus the derivative of 1, which is 0, equal to derivative of 0 is 0. So therefore, now we have a second equation. Oops. Now, since the question did not ask for dx over du and dy over du as a function, but simply asked you to evaluate it, what I'm going to do is simply plug in all the numbers. So at UVW equal to 1, 1, negative 1, and xy equal to 1, negative 1, what these two equations turn into? Well, the top equation becomes 2 dx over du plus y, which is negative 1, so become minus 1, plus u, which is 1, so plus 1 dy over du, plus v is 1, so plus 1 dx over du equal to 0. And this turns to this equation. So 2 dx du plus dx du becomes 3 dx du plus 1 dy du minus 1 equal to 0. So that's the equation that we have at this particular point. Now we look at the second equation that becomes dx over du plus dy over du plus vw. V is 1, w is negative 1, so become minus 1 equal to 0. So that's my second equation. So now notice that is much cleaner now because I don't have to deal with all the variable, but we will have to deal with them in our next example. So don't get too comfortable. But in this case, when we're evaluating it, I can just simply plug in all the variable so that now we can just focus on the partial derivative. So what I'm going to do is look at these two equations, and what I'm going to probably do is the following. I'm going to take the top equation. I'm probably going to keep it the way it is. And I'm going to negate the bottom equation into this one. And we'll add them. Notice that the dy du cancel out, the 1 and the minus 1 cancel out. Therefore, just leave me with 2 dx du equal to 0. Therefore, imply that dx over du equal to 0. So that's my answer. And because it's equal to 0, definitely make it a lot easier for us to do the answer, the rest of the problem. So I would say that dy over du should equal to 1. Because if you just look at what's boxed in right here, dx du is 0, so 0 plus dy over du minus 1 equals 0. That you can infer that dy over du must be 1. So that's my answer right here. Dx over du is equal to 0 and dy over du equal to 1 at the point that we want to evaluate. I think we'll stop right here for today. I do have one more example that I want to show you, but I guess we can do it on the next video instead of me squeezing it in and make this video too long. All right, I'll talk to all of you tomorrow on the next video. Okay, bye bye.